almost 2 years ago, the International Space Station was visited by Space Shuttle Endeavour as part of the last couple of flights to the International Space Station. That flight delivered the Alpha Magnetic Spectrometer, and yesterday, obviously, there was an announcement relative to the progress of AMS's experiment activity on the outside truss segment of the International Space Station, and we're very fortunate to have Trent Martin join us from Marshall Space Flight Center this morning. Trent, how are you doing?
Good, thank you.
Great. Well, Trent, just to set the stage, Trent's been, I guess you've been at JSC since, you said, 1995, I think, and you supported activities now through the JSC Engineering Directorate. But talk about your level of excitement based on what you heard yesterday.
Well, the entire team is excited. We're just excited to have the first paper published and out there. But really looking forward to all the rest of the papers that will be coming this year and then throughout the coming years. We've been gathering data since AMS was installed on Space Station almost 2 years ago now. And in fact, we've gathered over 31 billion particles, which the scientists have to cull through and identify specific science results that they'd like to publish. And fortunately, yesterday, the first paper was published.
How have you been following this? I know, you were integral and with the team that basically integrated AMS into the shuttle mission and got all of that going and got it obviously delivered to the station. But since that time, how do you keep track of what's going on with AMS? And obviously you're keenly interested in that.
Right. So I'm still considered the AMS project manager, but at this point we've essentially transitioned into operations. What that means is that on a day-to-day basis, the team that we have in Houston, which is fairly small at this point, coordinates with the collaboration who are operating the experiment out of Geneva, out of Payload Operation Control Center at CERN, and also at nighttime in Geneva, they have a separate control center in Taiwan that provides some operation support for them. So what we do is integrate the activities between those two control centers in Geneva and Taiwan with the control centers in Houston and the Payload Operation Integration Center here in Huntsville. And on a daily basis, just make sure that they're getting the data that they need, make sure that if there's any configuration changes to the space station that they need to be aware of, that we inform them of those. If there's some specific analysis or thermal or structural or avionics or data analysis that needs to get done, we perform that activity in coordination with the collaboration and then get the data back over to them. Essentially, we act as their single point of contact into NASA, whoever NASA may be, whether it's the space station program or others within the agency.
Well, you talked about the team right now being fairly small, but obviously there's a reason for that because things are going well, obviously. But it started out obviously as a much larger team, and there's a much wider distribution of the folks working on this, right? It's like you said, it spans kind of worldwide almost, right?
Yeah, we have as many partner nations on the AMS collaboration as the space station has partner nations. They're different nations, but it is a collaboration in that each one of those partner nations and institutes, of which there are 56, provide some component or some analysis or some computer resource to the collaboration. So essentially they bring a piece to the table, and then the collaboration led by Professor Ting from MIT works to coordinate those together. During the build-up of AMS, it was our job at the Johnson Space Center to ensure that those integration activities went smoothly, that we were able to build an experiment that could be launched on the space shuttle and then eventually installed on the space station. We provided the systems engineering and the integration function for the entire collaboration. They provided the pieces, we put them together in Geneva, obviously with a lot of their help. And so over the time, we had a team that was as large as 600 engineers, physicists, and technicians. My team in Houston now is down to just a few people, but the collaboration remains at a fairly high level. They operate the experiment 24 hours a day, 7 days a week, with, like I said, teams in Geneva and in Taiwan. In addition to that, they're gathering 1.4 billion particles a month, which have to be analyzed. So they analyze those at science centers in Geneva and then at various universities around the world. What they've done is they've broken up their science teams into two major groups so that they can actually double check any results that they're analyzing. So one group will check the results, the other, they'll meet on a regular basis and say, all right, we're looking at this particular issue, you need to go double check that before we publish.
Well, let's see, Trent, I don't know if we've got some video of some of the AMS activities associated with the launch and rendezvous and obviously the docking and obviously then the relocation of AMS from Endeavour, but it was a fairly intricate process, I'm assuming, and it started obviously way before the actual shuttle mission itself. That's how payloads work, but you were involved in this from the very beginning, right?
Right. I began working on AMS in 1995 in a capacity as a structural analyst, and then worked my way up as eventually as the project manager for NASA. But along the way, AMS-2, which is the version you're seeing here, was started in 1998, soon after we had completed our initial mission of AMS-1. It included upgrades to the detectors. I always like to say if you give scientists time, they'll upgrade to the latest and greatest instrument, which is what they did with AMS. So over the years, the different components would come together. We put them together and tested them in various facilities around the world, eventually culminating in the final integration in Geneva at CERN, in a clean room that was provided by CERN, and then tested at Noordwijk in the Netherlands at STEC, and then was sent to the Kennedy Space Center, where we finished off the final integration and installed it in the space shuttle and launched it in May of 2011. And you just saw it being taken out of the space shuttle payload bay and placed onto the starboard truss of the space station, what's called the S3 upper inboard payload attach site. AMS is not your typical payload on space station. It's very, very large. It's 15,251 pounds. It takes up an entire site where you would typically have, 4 to 8 payloads sitting on an express logistics carrier. And there you can see a nice shot of it right as we finished the installation in May of 2011.
That's a great view because that gives you talked about the size of it, but when you look at it on that space station, it really gives you a perspective of how large the space station is actually, because that is a large instrument, as you saw in the back end of the payload bay.
It really does give you that perspective, a really good perspective. And in fact, in that picture, you can see the PV arrays, the photovoltaic arrays of the space station behind AMS. And one of the things that we've had to deal with over the first 2 years, which we knew we would have to deal with, is the thermal cycles that occur on space station. Every 45 minutes, one side is hot, the other side is cold, and then 45 minutes later, it's reverse. As space station goes through its normal operations, those PV arrays rotate around, and from time to time, they shade various portions of AMS. And so with our over 1,500 thermal sensors, we're constantly monitoring the status of the experiment, the various components of the experiment to make sure that nothing is getting too hot, nothing is getting too cold, and ensuring that the data that we're collecting all the time is legitimate, useful scientific data. And so those PV arrays play a factor. There's large radiators on space station that are right next to AMS, which also play a factor into the thermal conditions of the payload itself. Here's a great view that was taken by one of our EVA astronauts during the installation of AMS. I love this view because you can see Endeavour, you can see AMS in the foreground, Endeavour in the background docked to space station. It's a good view from the express logistics carrier sitting right next door to AMS to give you an idea of where the other payloads are next to AMS. You can also see the radiators, the white in the bottom left-hand corner, those are the large radiators of space station that help remove the heat away from the components on space station that are too hot. And those play a factor in temperatures on the AMS itself.
Well, they have their work cut out for them with that. I think you mentioned 1.6 billion samples that they're getting per month right now. So they've got a lot of work that they're, I mean, it's just continuous. It's just an amazing number when you think about that.
Yeah, it's really, it's never ending. It just keeps coming. It's a large quantity of data. Yesterday I was fortunate enough to go visit the Payload Operation Integration Center here in Huntsville. As the data comes down from space station, it works its way through TDRS down to White Sands, onto Marshall Space Flight Center, and eventually across the ocean to Geneva. Along the way, there is a storage facility here in Huntsville where all of our data sits, and every bit of data that we've collected on AMS is sitting in one of those computers. In addition, we gather the data in Geneva and store it there, and we have multiple places where we store the data so that we can ensure its integrity and ensure that we never lose any of the data, because it's a once-in-a-lifetime kind of event. Once you've measured it, it's never going to happen again. You don't want to lose it. And as we're looking for various science, some of the science that we're looking for, including antimatter science, you're really looking for that one particle in billions. You may find that one anti-helium or anti-carbon atom, and it may be in that data that we already have collected. We just don't know yet because we haven't gotten to it.
And that's the fascination with this type of experiment, that you might not know yet what you're going to find out, and that's really just absolutely amazing. And Trent, I really appreciate you taking time out. I know you're busy up there in Huntsville, and we'll be glad to get you back to JSC when you get back, and we appreciate you taking time out to talk to us today. Thanks a lot.
All right, thanks. Appreciate it.